Yes, I have. I tested them out a couple of weeks ago, and I'm trying to get them built into what we're doing because I want us using them. Okay, so today we're going to be talking about lenses. And there are two kinds, converging and converging lenses are convex in some way. So to give you some examples of those, this is called plano-convex. Because on one side, it's a flat plane, and the other side bows out. So plano-convex. Yes? Yeah, I'm going to put this on YouTube also. Yeah, it's all good. Okay, plano-convex. You also have double convex. For those of you that wear glasses, if your glasses are thicker in the middle and thinner on the edges, you have double convex glasses. Well, you can usually see that it's how it's attached if you can see the lens connection, but your frame may not let you see if they're thicker on the outside. Yeah, I don't think so. Some people can, some people can't. You can also, huh? It's okay. It's okay. So usually what I would do is just slide my fingers across my glasses, which I don't have. So like if I can feel it gets thicker in the middle and then my fingers get closer together, that's usually how I tell. Except that I already know that I have, because I have a cataract forming in this eye is becoming more and more nearsighted. That doesn't happen naturally, by the way. You only become more nearsighted if you have problems with your eyes. Your normal thing that happens as you age is you get more farsighted. And then some people just can't see. Then the other one is called a meniscus. Meniscus. And your eyeball would be over here. So it's like two concaves or two convex sort of inlaid with each other. They are nestled behind each other. Kind of like a spoon, except if the spoon was a lens, it would have that shape. You can also hear this one called, and this is odd to call it this, but you can hear it a concavo-convex. Because this is physics and we just make up words if we want to.
Well, everything has a
yeah, it's just what roll with it. So that's a converging lens. So here's what I need you to think about on this. Let's imagine that Miss Wilson got bored in her English class in high school, because that never happened. And she started taking stick pins and sticking them through a sheet of paper like so. Because when you're bored in English class, you do these things. Hey, look, I've spent class periods counting and estimating how many holes I think there are in the ceiling tires. So, yeah, it's sad. I was estimating. I wasn't actually counting them, but yeah. So we have all these cute little stick pins with their little heads underneath and the sticky part up on top. So they look like a little forest of trees, something like this. Now, I'm going to have to change my backdrop really quick because you guys are going to not see that very easily if I do this. So let's do Let's go back to none real quick. Okay. So here's my sticky little piece, right? What happens if I stop share? If I take my little forest of stick pins that have been stuck through here, if I take this and bow it out, which would be a convex, right? Convex is bow out. What happens to the little stick pins? On the side facing you, that's the bowed out side, the little stick pins all start to face away from each other. But on the side that's curved in, they start to pull the pins closer together, right? So on the convex side, they spread the light out. On the concave side, they pull the light in. Now, that's going to be important here in just a second. So hang on to that. And we do this. So if we have bowed up, light would exit like so. But if we have bowed in and light is exiting like this, this is light exits and spreads. This is light exits and converges.
So after I finish this determining graphs, you want me to do the 3 labs and then?
Below it, yeah. If you have time, if you have other stuff you need to do, that's fine. Okay, so this is our converging lens. All right, this is going to be our converging lens. And you may be wondering about that because this converging lens looks like that. Okay, we'll talk about that when we get there. So, next kind of lens, diverging. Diverging lens, you have, what am I trying to write? Plano concave. Which would be a flat side with a curvature in this way. So the light is coming in from this side and it spreads out on that side. That helps. Probably should have done that in the other ones. I can go back and do that. So light in, spreads out on the back side. We also have double concave. And these are hard for me to draw sometimes because that bottom never quite looks the same as the top. So light in on this side, spreads out on that side. And then a meniscus again. Two curves stacked. And light in, spreads out. a meniscus, and some of you know this, you know, if you take water in a glass, I know you can't see this very well, but you let it sit, it makes a little dome on top. That dome is called a meniscus. That's where that word came from. It's because water is very adhesive and not cohesive. Co means with, ad means with something different. So adhesive, so Band-Aids are called adhesives. They stick to something other than Band-Aids. I mean, we all know they stick to Band-Aids as well, but you know what I mean. Whereas water is not very cohesive. It does not stick to my skin very well, but it sticks to other water droplets really well. It's kind of that. So now we need to do ray diagrams, but first, the math. Because today is our note day. Yay, notes. Here's the math. Math with lenses. Hey, look, it's the same equation. But there are some changes. For mirrors, what does a negative sign indicate? I've got a lot of hand waving going out in the room. Y'all are probably doing that at home too. Negative sign means where? It is behind or in the mirror. So here's your new one. For lenses, a negative sign means on the object side. Of the lens. So if your image and your object are on the same side, the image will get a negative sign. Say that again. With lenses, if your image appears on the same side as the object was placed, it's a negative sign for your distances on this equation. Because where should light go on a lens? Should go out the other side, right? Should come up to the lens, pass through the lens, go out the other side. So you get a virtual image on a mirror when it's behind the mirror because light can't go there, which is negative. But on a lens, you expect the light to go over there. So if it stays over here, you have a virtual image and a negative sign. So in general, the easier way to think about it is if you have a virtual image, your sign will always be negative. But you will have to pay attention to converging, diverging about the focal points. Okay? So a converging lens has a, let's see, converging lens, we're using the one on the other side, has a positive focal distance. Diverging has a negative. Okay. And the last bit of math is that magnification equals what? There were two of them.
Well, image, original image, S over S I, right?
I over O
And high.
Other than, yeah.
and hi ho. Hi ho. Hi ho, hi ho. So none of those changed. But the sign conventions have changed, okay? Remember that on this, if you're talking about magnification, what does a negative sign mean on magnification?
You're right. It's, it's upside down or right there.
Right, is inverted. Negative means negative magnification is an inverted image. And then we got to do ray diagrams. Lots of ray diagrams. Okay. And I'll wait because I know some of y'all are still writing, so I'll wait for you guys, these people out here to finish and you guys out there to finish, and then we will. Oh, where did my chat box go? There's my chat box. In case I need something. You guys have a chat box, so you're welcome to talk to me if you need to. Or unmute, whatever makes you happy. Emily, I'm sorry that the computer keeps deleting your test grade and quiz grade and grades in general. What the heck? Seems to be picking on you, though.
Mr. Hart,
That's fine.
class because it deleted all the grades that we put in.
Nice. Sarah Ruth Welliver just said that she has the exact same problem you're having, but in Mr. Hardison's class, so at least it's not just me.
Mr. Hart was like, that's not right.
And they fired the head tech guy at the county office yesterday, evidently. Yeah, well, Andrew Campbell said it's a kid. He said, my friend Jack, it's his dad. So I don't know who that is, but that's not good for family right here before Christmas. But I can totally understand why that happened, because you have to blame somebody, unfortunately. And AT&T is hard to fix. All right, so let us move right along to the ray diagrams. Okay, here we go. So I hope whoever that was didn't get fired. I hope that's just a rumor. And obviously I don't know who that is. So it'll probably be on the news tonight, like the Daily News Journal. All right, so here we go. Ray diagrams. Let's do it. We're going to start with converging. So ray diagrams, we almost always draw a lens like so. And then they tell you that it is a converging lens. Now, what does this really look like? So we're going to have two focal points. Lenses have two focal points. Mirrors only have one. They have two. So here's focal point 1, focal point 2, because this lens is actually bowed out on both sides. So this is like a zoomed in, and it would have double concave, just to use the easiest one to work with. Double concave. So the focal point F1 goes with this side. The one I've labeled F1 goes with the right-hand side of the lens, if you will. And F2 goes with the left-hand side of the lens, because you always have your focal point inside your curve. So this one gets paired with this one, because the focal is inside your curve. So to draw the other kind, if they tell you, oh, that was not very even. If they tell you that this is a diverging you have to think that it's thick and curves. Oh, that was terrible. I can do better than that. That's not great, but that kind of illustrates what we've got going on. So the curvature now would be this point goes with this side, and this focal point goes with that side, because you stay inside your curvature. And that's a very uneven lens. That would be like maybe somebody with an astigmatism. I have astigmatism.
I can't see.
Astigmatism indicates usually that your eyes are a little squashed.
No,
And everybody's eyes get a little squashed as they get older.
it's a little squishy.
Yep. So everybody gets a little bit of that. You can tell if you have it because words wiggle on the page when you try to read them. It's very frustrating. So your eyeball is just a little bit like this, and because your eye traces triangles all the time, then it offset the numbers or the letters get offset on that next glance, and so it looks like the letter is doing this or marching across the page.
I always read the same line twice. Like I read a line, you
Uh-huh.
look down, and you feel like you didn't move.
You're right. Yep. I understand that. I had no eye problems until I turned 48. And I'm starting to have some eye issues now. Okay, so now let's do the ray diagrams. Okay, here we go. So this is going to be we're going to start with converging lens. So F1, F2. Where do you want to put the object? Inside focal or outside focal to start with as our first one? Outside? Okay.
Outside the box.
Think outside the box. So here's our object, which means everything on this side with the object is negative. If you're using anything on that side, the object is positive, but everybody else would be negative. So this is now the positive side for distance, because we expect the light to go through the lens and come out the other side. But with the mirror, we expect it to hit the mirror and bounce back. So in front is positive and behind is negative. So what are our rays that we draw? We're using the same rules we use for mirrors. So what rays do we draw? The one that comes in parallel, what does it do? Out through the focal point. Which focal point?
2.
It came in from, the curve was on the side with the object, so it's going to curve here.
Because it is not dive.
Yep. Because the light came in on this side, and the curve of that side is bowed out. So its focal point is the one on the other side. So this is where we have to be a little more specific on our in parallel. So for converging lenses, in parallel to central axis, goes out through the opposite side focal. It's our first one. What's our next one? In through the focal point goes out parallel, right? So it's got to come out parallel. So it's going to go in through the same side focal point now. In through same side focal, goes out parallel to the central axis.
How do we know which one's the
Huh?
How do we know which focal point?
Okay. Which side does, oh, that's not going to be the best way to say that.
Where the light comes in?
Yeah, it's determined by where the light comes in. So if the light comes in parallel, it came from the focal point with that side, which would be the left-hand side. So the focal point would be on the right. Here, look, kind of got that? You kind of have to think like, kind of bowed out. So when I come in parallel, the focal point that goes with the side I came in from is on the right. Because our lens is kind of doing this business. The other way to think about it is it pulls the light rays together because it's converging.
Yeah.
So they should, whatever goes in has to get closer to the other thing that came in on that from that side. The easiest one, okay, so let me write this one. So in central altruist, opposite side focal. So in through same side focal goes out parallel to principal axis. So same side focal turns into a parallel. And then the third ray, which we never used with mirrors, but it's very useful with lenses. I think I told you that when we talked about mirrors, is the one that passes through the midpoint completely unchanged. Oh, line, please. Thank you. The one that goes to the exact midpoint doesn't get changed at all. So we call this a central ray. So it goes through the middle of the mirror, or the middle of the lens in this case, and it does not get deflected in any direction. So where does our image form? Where all of those exiting rays intersect. All the exiting rays intersect here.
So all three should hit the same spot.
Huh?
All three should hit the same spot.
Yes. And if I was doing this with measurements, I'd probably have them all the same. But what this tells me is my focal points are a little different distance from the lens, or I wasn't really quite even with lines. So hand drawn it, they're close enough. Because theoretically, you're all originating from the exact same point in space. which clearly I can't do with a thick marker or a pen or pencil anyway. So yeah, but that's kind of the idea. So what is this? In real life, what did we just draw? What object is this? It's something where, like the focal distance, the things that are out there past the focal distance show up upside down.
Our eyeball,
Ah, there we go.
yeah, everything in your eyeball has been flipped.
This is your eyeball. And then the optic nerve flips it for you.
Brain has to do all the work.
But so where is the focal, what's the focal distance for our eyeballs? Our focal distance for eyeballs is very small, right?
So you can like find it, you sure it's like.
Yes, you can find it by moving your thumb. Because you'll lose the image of where your thumb is at some point, right? If you come straight in. But having said that, the focal distance is really close to your eyeball, so everything in the real world is out there. Because the way our eye works is the image is projected on the back of the eyeball at the optic nerve, and it's upside down. So our brain flips it right side up and interprets it for us. Okay? I'm waiting for just a minute to see if they have any, if we still writing. Anybody still writing in here? You good? Okay. All right. Let's do another one. This is my line maker. Line maker. This time, let's put our focal points out here. Yeah. Okay, so now we're going to put our image or our object in here. Let's put our object is now going to be inside the focal distance. Oh, do a line. I'm struggling. There we go. There's our object. And by the way, F1 and F2 don't mean anything other than there's two focal points. Like there's no, I'm not labeling because one's on the left and one's on the right, or one's for the right hand side, one's for left hand. I just label them.
Make sure to label, so they're not just.
They're the same distance on each side. So unless you want to make drunk goggles. And then the drunk goggles, sometimes you have the curvature on one side doesn't match the curvature on the other side, so that the image appears out of proportion. So you mess with where the focal points are. Like you make one really close in and one far out, and then it's just get a weird image.
Yeah, it's not like you reach out and think it's close, and then your hand is going.
Right.
One of them we did was kind of like made everything like either up or like down.
How about the upside down goggles where like they have the mirror that flip?
No, the drunk goggles, they had like the highest setting,
Uh-huh.
and, like put them up or down, so like when you were walking, you couldn't like, it was.
You were struggling to know. It looked like you
rolling.
should be climbing and you were,
Yeah.
yeah, okay. Now I follow.
I also put a pair of jump goggles on top of a pair of jump goggles. That wasn't fun.
Yeah, that probably makes it pretty interesting.
That is called.
That was just not.
So, all right, here we go. Let's see if we can do it. What's the easiest one to draw? The easiest one to draw is the central ray.
So it goes down the middle.
Because what happens?
Ooh, you know where it's gonna be.
It doesn't do anything. It just keeps on trucking. So for mirrors, this is the easiest. Or for lenses, this is the easiest one to draw. For mirrors, we don't use this one at all because it's usually a pain in the tail to get the angle. Okay, now what do I do? In through the same side focal. In through same side focal does what?
Arrow,
Goes out.
arrow.
parallel. Now what about the last one? This is the one that's a little trickier, but not too bad. It goes in parallel. And where does it go?
To the focal point.
On the opposite side.
Oh, yeah.
So what happens now?
Where's the fiction at? You gotta do it the opposite, like the brain thing.
We have to figure out what our brain shows us now, right? That's the tricky bit. So on this side, we have no intersection. So that means we have to backtrace. I shall backtrace using green. Okay, I'm going to backtrace using green. So where does this top blue ray appear to our brains to have come from? It comes from, actually, let's make that lime green so it's easier to see. It thinks it came from there. Where does our brain think the red ray came from? Straight back along that same line, right? So our brain does the back trace. So where is our image now? Because the central ray does what? The in and out are the same thing, so you're there. So where does your image actually appear now? Somewhere where these three are intersecting, right? So I'm going to go back to the other one in just a second because we didn't do our classification, so we need to do that. Okay, so hang on for just a second. What do we classify the image as? Real or virtual? This one is real because the light went there. Is it closer or further? This one looks a little further. I'd like to have a ruler on that though. To be sure, I'd like to have a ruler there. What about inverted or upright? Inverted. Larger or smaller? I feel same to larger. Okay. Maybe larger, maybe same. It's close enough that once again, I'd like to have a ruler. So what's the classification for this guy? And then you need to tell me what this image is. Image is, what is virtual? It is further from the lens. It is upright. And this one is clearly larger. What object is this in real life? Where you put something really close to the lens and the image is really big.
Magnifying
This is a magnifying glass.
Oh.
It's a magnifying glass because you put the lens close to the object you want to look at and you see a bigger version of it as if it was on this side of the lens. The same side as you are.
Is that how microscopes work?
Yes.
Put a bunch
But-
of
but-
Except-
refractive lenses.
Yeah, backwards.
Um,
Well, not backwards. What you do is you use a mirror on one place and you can do it two ways. You can either use two lenses that both magnify it, or you can use a mirror and a lens.
Isn't that how telescopes work too? Where they
Telescopes too.
reflect it off a mirror. and
So a
then-
refracting telescope is two lenses. And then a mirror to your eyepiece, but it's a flat mirror.
Yeah, it's like that, and it goes-
Reflecting telescopes use a lens and multiple mirrors that are curved to get the bigger, and then the last one is flat to project the image to you.
what benefit do they get from mirrors rather than just having lenses?
It's easier to make a mirror than it is to make a lens. It's easier to get the curvature right.
and then you bounce it.
So when you're grinding a lens, you have to get it very, very, very smooth. A mirror you have to do as well. But a mirror basically is just a sheet of glass and you paint the back of it with silver.
Yeah.
And that's a lot easier to do physically manufacturing than it is to make the lenses, where you have to get them in the little molds and then get all the air bubbles out and sand them. And so reflecting is the kind that's been around longer. But refracting tend to be a little bit higher quality images, because you do lose some of the light doesn't all hit the next mirror.
Yeah.
So it tends to get fainter as you come back, but not enough usually for it to matter. I have what mine looks like a pot belly. I have a 4.5-inch telescope at my house, so I can see the rings of Saturn on a good clear night. Mars looks really good right now because Mars is up there by the moon. You can get a really good look at it, and it's very red. But 4.5-inch telescope will usually let you see the rings of Saturn without too much effort. But mine is a pot-bellied one, so it looks like a cannon, like the front end of a cannon, nice big circular tube cylinder connected to a sphere. So mine has mirrors on the inside surface of the sphere at the bottom. So it's only about this tall, but the lens that the light comes in through is this big. So when I put it's 4.5 inches in diameter. That's the reference on a distance is the diameter of the lens. And so I have to put a moon shade on it, because if I look at the moon through my telescope, it's blindingly bright. So you do what's called a moon shade, which is basically just a lens cap that's got a smaller hole inside. So it blocks out a lot of the light so that you don't go and burn your eyeballs from the moon, which people go, you can't get your eyeballs burnt from the, yeah, you can. If you're looking at it close, it's reflecting a lot of the sun's light. This is pretty intense. Okay, so how are we feeling about this? Okay. I'm going to have to come back because we get out at 12:15. We'll do the diverging lenses when we come back. We'll do that at 12:50. 12:50. So I will start then, unless I don't have everybody back, in which case I will wait for you. If you don't want to come back, I understand that. I will be putting this video up on YouTube this afternoon, so you're good either way. I would recommend coming back though, because you need to hear the explanations and maybe ask questions when you see it the first time. So this is part